I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. So I wanted to take just about an hour or so with you guys just to tell you some of the rudiments of partial differential equations. In some sense, give you an advertisement for a course we don't offer. Well, not yet anyway. Who knows, maybe in the next couple of years there'll be enough engineers around these parts to offer this course. But partial differential equations are really important because all of the major equations in physics really are partial differential equations. So just to give you a brief sort of rundown of a few of them. What's a partial differential equation? So we get sick of writing that pretty fast, so we instead say PDE. Right? So a PDE is just kind of what it sounds like. It's an equation, a differential equation, which involves more than one independent variable. So it involves partial derivatives. So let's see here. Like, for example, if V is the voltage, then in a region without charge, you have that the Laplacian squared of the voltage has to be equal to 0. Now this right here, you could write as like the partial x derivative squared plus the partial y derivative squared, the voltage equal to 0. A lot of times we use this notation, Vxx plus Vyy equals to 0. So this is the so-called Laplace's equation. In the plane, so this would be the equation the voltage function has to satisfy if we're talking about the voltage in some two-dimensional region. Of course, if you have this is no charge. If there's charge around, so rho, usually use rho for dV, dq, or excuse me, the other way around. So rho is the charge per volume, the charge density. So if this is not equal to 0, then we have what's called Gauss's law. The divergence of the electric field is equal to the charge density divided by epsilon naught. This is the Gauss's law. Now you guys study that in physics too, usually at the level of integration. You look at the flux is equal to the charge enclosed. That just comes from integrating this differential equation over a volume and using Gauss's theorem. But this is related to Laplace's equation in the following way. The electric field is equal to minus the gradient of the voltage function, right? So if you take the divergence of the electric field, that's the same as minus the divergence of the gradient of the voltage function, right? Now this, the notation for that is the Laplacian, and there's a minus. And on the other hand, that's equal to the charge density divided by epsilon naught. So there you go. This is what's called Poisson's equation, which states that the Laplacian of the voltage function is equal to minus the charge density divided by epsilon naught. So this is the differential equation that you have to solve in the presence of charge. If you got charges around, you need to solve. This is called Poisson's equation. So like Laplace's equation, special case, right? Tons and tons is known about how to solve Laplace's equation in all kinds of different geometries and situations. People study how to solve these equations in all kinds of wacky spaces, really. But all right, so these are some partial differential equations that are important, obviously, to the study of electricity and magnetism. Another thing I always show Calc 3 is this: if you have the curl of the electric field, what do you get? What's the curl of the magnetic field? What's that? I'm trying to remember. Let's see, this one is mu naught times J. Now that gives you, J is the current density. That, what I've written so far, gives you what's called Ampere's law when you integrate it around some integrated over some surface and apply Stokes' theorem to the boundary, you get the Ampere's law. But there's also this term that Maxwell added about 1860 or so, epsilon naught partial E partial T. This is the so-called displacement current. And that's important for reasons I'll explain here in a second. But Maxwell added this term. That's why they're called Maxwell's equations. By the way, this right here is one of Maxwell's equations. This is another. This is Ampere's law with Maxwell's correction, I think. And let's see, this one, I believe, is just. Oh man, I'm forgetting. Curses. What was that one? It may just be minus partial B partial T. I'm a little bit fuzzy on the signs here, and I feel like I might be missing a multiplier. But anyway, I won't bore you with the whole story. But if you take my Calculus 3, we study the relation of the curl and the divergence and how these work together. And from these, you can derive wave equations for the electric and magnetic field. And the wave equation, if I remember right, is something like this. Partial squared E, partial, oh man, I can't remember. I guess it's got to be partial x squared. Oh, uno momento. Let's smudge them. So it's the Laplacian, I think, of the electric field equals to, I want to say, 1 over mu naught epsilon naught partial squared E partial T squared. So in the plane, this, or in 3 dimensions, this would look something like the x derivative squared plus the y derivative squared plus the z derivative squared acting on the electric field equals to that. Now this actually gives you what's known as this is a 3-dimensional wave equation. Let me try to explain to you why that's a wave equation for the electric field. It's a wave equation where the speed of the wave speed is equal to the square root of, excuse me, uno momento. I've got the units on this right. I think I'm not 100% sure on this. It's been a little while since I'd have to do it. I think that's actually supposed to be mu naught epsilon naught upstairs, because the speed is supposed to be what we call it c. It's 1 over the square root of mu naught epsilon naught. Here, mu naught is the permeability of free space, and epsilon naught is the permittivity of free space. They describe how the electric and magnetic fields propagate through space and time. But this equation is very fascinating because it says the speed of the electromagnetic wave is given by 1 over the square root of the permittivity and permeability, which is kind of shocking because it has nothing to do with really the frame of reference per se, right? It just has to do with free space itself. That's kind of surprising. But this is maybe the first mathematical evidence that the speed of light is constant. It's an indication of it anyway. And that just comes from Maxwell adding this term to the Maxwell, well, to what we call Maxwell's equations, but really to the differential equation, which describes how the magnetic field couples to current, and also to the electric field. Let me try to explain to you why that's a wave equation, though. So suppose you have a string, right? And suppose that the string is taut, really tight, right? And you want to study how does that string wave up and down. So what you do is you look at a little segment of it, like this, all right? And this segment is going to have mass m. So I think I'll put this point at x comma y, and this point over here will be at x plus delta x, y. Oh, I'm going to regret putting that label there. This board is not helpful. X plus delta x, y plus delta y. I'll try to get through this fast. I don't really want to burn too much class time on this, but how many of you have seen the wave equation derived before? Yeah, So the idea here is the thing that makes the string wave up and down is completely the tension of the string. We can effectively ignore gravity because gravity acts the same over the little length of segment of string. And we're just going to focus our attention here on one little piece of the string, because if we can figure out how it works for one little piece of the string, then we can extrapolate that. Since no particular little bit of the string is special, that differential equation must hold for the whole string. That differential equation we're going to derive is what's known as the wave equation. And so the thing that's making it wave up and down is the tension, right? So there's the tension here and there's the tension there, right? Equal magnitude but opposite direction like that. And let's see here if I can draw the right picture for us. Stop that. Stop, don't move. All right. So my observation is that the y component of, I'm going to call this one T2, let me call this one T1 just to keep them separate. But of course you can break this into two pieces, right? There's T2x, T2y, right? And over here you've got what? T1x and T1y, right? And by the way, the mass, well, let me not distract myself here. So how is what's the geometry here we can say? The ratio, right, of F1y, let's see here, F1y, excuse me, T1y, divided by T. Let's see here, what is that? Oh, I guess I should say T. Okay. Divided by T2. I guess I could say divided by T1x and my T1x, right? And on the other hand, I have T2y divided by T2x. What are these going to? How are these going to be related to the slope? I mean, those should be related to the slope of the little bit of string we're thinking about, right? What would the slope of the string be? If you think about this little string right here, what is? I mean, so it could have. I mean, I'm not doing the slope. This doesn't. The slope could be different here and here. I mean, I'm not doing. The string could be all kind of wavy, and it could be that the little bit we're looking at, you've got a different slope here versus there, So my zoom in picture is a little bit too simple because we could have different slopes at the endpoints. So they don't have to be equal. They could be different. But they should be related to the ratio of the y component and x component of the tension in the same way geometrically as the slope of the string, right? Like the tension pulls tangent to the string. That's how it works. So here, T2, that should be partial y, partial x at what point? At this point, right? And how about over here? Over there, it's going to be minus partial y, partial x at the point x comma y. Yep. Do I have I reversed the? Oh no. Well, here, I can easily let me fix it this way. I did the same thing yesterday in Calc 2 with something like, I don't know, I just, I almost got held back a grade because of my dyslexia. Now, my mom disputed the dyslexia. She said, people with dyslexia don't have like 3rd grade math skills in 1st grade. She's bored with your teaching. But I don't know, maybe they're right. Maybe I do have some, I don't know. This is a popular mistake for me. Thank you for fixing that before I went too far down the trail there. All right, so then what do we know? It's a length of string. It's got tension pulling on it, right? But this little mass, this little string, it has to be subject to Newton's law, right? So the mass, you could say, is equal to the mass per unit length, mu, times delta x, essentially. There's a little bit of a cheat right there. Right, a little bit of a cheat right there. But Newton's second law says that m d squared y dt squared, which in our context would be mu delta x partial squared y partial t squared, should be equal to what? We're just looking at the y component, right? So it should be equal to basically, these two guys. See here. Oh. So there's a simplifying assumption being made here, basically, which is what? We're assuming that delta y is pretty small. So it's not being jerked too violently, let's say. So delta y is pretty small. That means what? That means that, first of all, the length here actually would be what? Delta x squared plus delta y squared, right? Square root. So that's two pretty good approximation, delta x. I've already used that in saying that the mass is mu times delta x, not mu times the square root of delta x squared plus delta y squared, which actually would be closer to the real length, right? But then the other thing that allows you to do is to say, oh, well, basically the net tension is essentially just the x part, right? So like this also implies that T1x is T and T2x is T. I'm just thinking about magnitudes here, of course, but I think I put the all my tension components are taken to be positive, and I'm using the direction to add minuses, So, yeah. I mean, if I was going to say T1x was negative, I wouldn't have to put this minus here, is my point. All right. Anyway, so T1x is approximately T, T2x is approximately T. That means that, okay, so Newton's law would say T2y, right, minus T, T1y. And, but of course, anyway, let me just get to the point here. So what I get is T times T times partial y, partial x at the point x plus delta x, comma, y plus delta y, minus partial y, partial x at the point x, comma, y. I guess I really shouldn't put the minus here then, right? Sorry. I'm coming to terms with my own sign conventions. This minus doesn't belong. If I put the minus over there, it's got to either go here or there. If I put a plus here, I could put a minus here. If I put a plus here, I could put a minus there. But the end has to be that, if you think about it. And then what? So then this gives us that partial squared y, partial t squared, equals to, let me bring all the constants over here. So I've got a mu mass per unit length divided by t, the tension, right? And that's going to equal to 1 over delta x. And then I've got this, well, let me write it this way, big fraction. Partial y, partial x plus delta x, comma, y essentially. Because again, delta y is so tiny, let's forget about it. Or you can think we're taking the limit as delta y goes to 0 if you like. But the point is that's what we get, right? So what happens as the length of string gets really small, what differential equation do we obtain? What does this fraction become as delta x goes to 0? See, we're taking the difference of the derivative of x, holding y fixed, and changing x. This is exactly the second partial derivative of y with respect to x squared, right? And so there you go. That's the wave equation. Partial squared y partial t squared. We try to write it in the same way I wrote this one. I think I have. So let me... So if we have partial squared y partial x squared equals to, let's see here, mu over t, partial squared y partial t squared. So by dimensional analysis, this is what kind of factor is this? So basically you've got a division by like meters squared over here. You've got division by like seconds squared over here, everything else being equal. So basically we must have that t over mu is something like meters squared per second squared. So it implies that something like v is equal to the square root of mu over t. That's the speed of the wave. Which makes a lot of physical sense if you think about it, because so mu is the mass density, right? So it says the heavier the string is per unit length, the slower the speed it propagates with. And then T is the tension, which says that the tighter you pull the string, right? Well, wait a minute. That seems wrong. Well, I got mu over t, just like that. Just my intuition is messing with me. V is squared. I've got v is square root t over u. Oh, well that makes more sense. How have I? Oh, look, I'm an idiot. It's just this arrow right here. Look, see? Good grief. It's a good thing the semester's almost done. It's getting worse. All right. There. That makes more sense, right? The more tightly you pull the string, the faster a wave on the string goes, if you think about it. If you've ever just played with like a jump rope or something. And then this makes sense as well, because the heavier the rope is per unit length, right, the slower the speed gets, because this division. All right. And this is a wave equation with speed. The speed of the wave is, again, v, which is the square root of the tension divided by the mass density, mass per unit length. This is the one-dimensional wave equation. And you can see why, if you go through the calculus 3, you get a three-dimensional wave equation And I hope you can understand why we claim that that has to do with the speed. I mean, I don't think I've completely explained it, but let's see here. Like a very easy solution to this wave equation is given by what's called Dalembert Solution. So let me make the equation a little bit easier for us to stomach. Can I erase this? I think I can erase that before you guys find any errors in my work. Hey. I try to cover that when I teach physics. I think Dr. Skambordis does as well. Some semesters. So if we have the equation partial squared y partial x squared, I can put the v squared over here. Partial t squared. Then if you look at y as any function of x minus vt plus any other function g of x plus vt, that will solve this wave equation. Why? Well, take some partial derivatives, right? So what's yxx? So basically just ordinary partial derivatives. And this f and g are arbitrary functions. Right. They have to be differentiable, like twice differentiable, right? But so, okay, that's the two x derivatives, because the chain rule doesn't do anything interesting. When you differentiate the inside function with respect to x, partial differentiate the inside function with respect to x, what happens? Nothing. It's x plus or minus vt, right? On the other hand, when we take the y sub t is what? Well, that's f prime of x minus vt partial t of x minus vt, right? Plus g prime of x plus vt partial t of x plus vt by the chain rule. And what happens there is interesting. I mean, this gives us minus v f prime of x minus vt, right? Minus, or rather plus v g prime of x plus vt, right? What happens when you differentiate one more time? What's ytt? So you get a minus v squared f prime prime of x minus vt plus v squared g prime prime of x plus vt. In other words, you get v squared times f prime prime of x minus vt plus g prime prime of x plus vt. Now, so you look at it, what is this? This is v squared times yxx, right? Because I have up here that the second partial derivative with respect to x is that, so that's exactly this, right? And there you go. That's a solution to the wave equation. This is called Dalembert's solution. I don't know how to spell it. Something like that. But this justifies my dimensional analysis that that's the speed as well, right? Because can you understand what this is like graphically? Let's just set g equal to 0 for a second, all right? And suppose that f of x, y equals f of x looks like this, right? Suppose that's y equals to f of x, right? Here I'm looking at y, here I'm looking at x. So we can think about the solution to the wave equation by animating it, right? I'll use color coding to animate it a future time. Think about it graphically. You've got y equals to f of x minus vt, right? So what is that? That's the graph y equals f done what? Shifted to the right, vt units. So it's exactly this traveling waveform. So it's the same shape, but so this is, if I'm matching up this point here, this is Vt later. So here you're looking at y is equal to f of x minus Vt. So this says that if you have some initial pulse in the string, then it just travels like that. That's the traveling wave solution, Dalembert solution. And the other one is left-moving waves, right? But it's pretty interesting because one of the things there's an interesting connection between these kind of solutions to the wave equation and then the ones that are like if you tie the string, if you fix it at two endpoints, right? And you have boundary conditions on the string, like you keep two endpoints of the string fixed, then you get these bounded solutions. And there's a relation between those kinds of solutions and these like infinite solutions. That's interesting. And well, I can't talk about everything today, but so that's the wave equation. It's interesting, of course, because, as I say, it helps us understand Maxwell's equation says the speed of light is constant. Let me talk to you guys a little bit about the, should have brought my cloth. This just is not as good. So let's think about, the other equation you spend most of your time solving in the first course in partial differential equations. Generically, they're I guess diffusion equations, and they sort of describe how something diffuses. So, for example, the heat equations, maybe the central example. And let me talk about the heat equation here for a few minutes. So the basic thing you study is something like you have some metal rod or something, right? And maybe here's x equals to 0. Here's x equals to L, all right? And you take a particular point, and you can study u of x comma t. This would be the temperature at time t at x, right? And then you study, if you have an initial given temperature distribution on the rod, then how does it cool? So that's what the heat equation describes. And typically some boundary conditions are given, like you suppose that, one simple homogeneous boundary conditions are nice. So for example, you can assume that u of L comma t is equal to 0, and u of 0 comma t is equal to 0. So like fix the temperature at the endpoints to be 0 for all time. These are so-called homogeneous boundary conditions. And then you're given, say that u of x comma 0 is equal to f of x. So this is some initial temperature distribution. And then the question is, what happens after that? You let it go. What happens to the temperature then, So you can derive that the partial differential equation which governs this is a so-called heat equation. And the heat equation looks like this. Uxx equals to some constant times ut. This is the so-called heat equation. Let me hazard an explanation for why this is the heat equation and what it's describing. So in one dimension, right, the gradient of u in one dimension is what? It's a one-dimensional gradient. It's kind of dumb. It's just partial u, partial x. I'm talking about the spatial gradient. And so what does that describe? That describes the change in u, right? The change in temperature as a function of x, right? So if you look at the Laplacian here is actually uxx. So in some sense what this is saying is the divergence of temperature is proportional to the rate of change of the temperature or something like that. This ends up being something like heat flow is proportional to the change in temperature, all right? So the question then is, how do you solve these kind of problems, right? So here, I'll walk you through it. So basically, the method is called separation of variables. And so the idea basically is this. Find a marker that works. You suppose that you can write the solution as a product of a function of x and a function of t. All right, so like, basically say, okay, so suppose you could write u of x comma t as equal to, say, x, which is just a function of x, times t, which is just a function of t, right? That's like the starting guess. Suppose we can do that. Maybe that can simplify things. So what happens then? And we're gonna set alpha equal to 1, okay? For our convenience today. Okay. So we want to solve uxx, which is what? So that's a derivative with respect to x 2 times of x times t. But the thing is, you can pull the t out because t has no x dependence, right? And so this is really just x prime prime t, where we understand that primes on x's mean x derivatives, right? And on the other hand, u sub t is partial t. Well, this time the x pulls out, really, right? Because x has no t dependence. And so we just get xt prime. So you put those things together, and that gives you that x prime prime t is equal to xt prime. And then what you do, because we don't like to try to solve 2 variables at once, is we divide by xt. Assume that you have a non-zero solution, all right? So suppose the solution that we're looking for is non-zero. Then we get x prime prime over x is equal to t prime over t, right? Which is a really, really neat equation. Because, why is this a neat equation? This right here, guys, function of x, right? This right here is a function of t, right? That seems like a contradiction. How can you have something that's a function of x equal to a function of t? Isn't that impossible? Apparently not. Yeah. What's the thing we sometimes are a little bit careless about when we talk about functions of time and functions of space or something? There is one kind of function which is universal to all different variable choices, which is constant functions. Right? The only way it can be both a function of x and a function of t where x and t are independent is that it be a constant. So this is equal to some constant, say k, often called an eigenvalue for the problem. Not the same kind of eigenvalue that some of you understand. Sorry, too soon? Let's see here. No, generally speaking, you guys did pretty well in test 3. I will try to get through this. I'll got about 5 more minutes of this, and then I'll maybe 10 more minutes, and I'll talk about your test. So then you see what we have is we have 2 related ordinary differential equations that we have to solve, right? So apparently, separation of variables says we had to solve x prime prime minus kx equals to 0 and t prime, minus kt equals to 0. Now this is easy. We can solve that just straight up. That's t of t is equal to e to the kt. Right, done. You could throw a constant in the front if you wanted to, but we won't for reasons that'll become clear shortly. So that's fine. We've got our time solution. There it is. Exponential dependence on time. Now, how about this though? This is where our boundary conditions come into play. We've got boundary conditions that and let's see here, to make things simplest, I think putting L equal to pi makes the math the easiest. So let's put L equal to pi. So we've got u of pi comma t equal to 0, and u of 0 comma t equal to 0, and u of pi comma t equal to 0. Right? So what does that translate into for the separation of variables solution? It translates into x of 0 times t of t equals to 0, x of pi times t of t equals to 0, right? T of t is non-zero, right? So that's not even the issue. So we really just obtain the so-called boundary value problem for the spatial component. In particular, we get x of 0 equals to 0 and x of pi equals to 0. So this is a boundary value problem. I think you asked me about this, Austin, right? So here's how it appears. And the question is, how do you solve those? We haven't solved those. All the problems we've done this semester, I think, pretty much, have been about initial conditions, when we're given a velocity and a position at a particular time. Now I'm given the position at I'm given the value at two different values of the independent variable. Okay, but, so then you're like, okay, well then what do you do? We break into cases. There are 3 cases. There's k equals to 0, there's k less than 0, and there's k greater than 0. It turns out that k positive and k 0 are not interesting. In other words, there are no non-trivial solutions to be found there. The middle case, k less than 0, means that k is equal to minus beta squared for some beta positive. And so we've got x prime prime plus beta squared, x equal to 0. And so that gives me what? That gives me x of x equals to something like a cosine beta x plus b sine beta x, right? And then we can figure out what happens here. What happens with x of 0? So the sine of 0, we get no information about b, right? Because this is 0. Cosine of 0 is 1. So we get, oh, check that out. So a has to be 0, right? How about pi? What does pi tell us about the solutions here? So apparently just b survives, right? So we got b sine of pi beta equal to 0. And so in order for that to be 0, we either need b is 0 or we need sine of pi beta is 0. We can't have b equal to 0. If b is equal to 0, we're back to the 0 solution, which is not what we're interested in here. We're after non-trivial solutions, right? So we need the sine of pi beta is 0. So what does that tell you? Yeah, beta is an integer. Sine of pi beta equals to 0 implies that beta is equal to n, an element of the natural numbers. I can't put beta equal to 0, right? That gives me the 0 solution. And I can just as well avoid negative solutions because they don't add anything. They just add minus the solution I already have for positive values. So why not just stick with natural numbers? They're natural after all. And so we get this solution then that so going back up to here now, we get that un of xt apparently is some constant. Well, we can set, I guess you could say b sub n if you like, and e to the, sine, what do we say beta was? Oh, sine of, how's it go? Let's see, where was I? Oh yeah, sine of beta x. Beta was n, right? So sine of nx, right? And then what does this say about k, by the way? This is k, which is equal to minus beta squared, is equal to minus n squared, right? So e to the minus n squared t. So Fourier understood this in the early 19th century, that you could find these so-called solutions, these boundary value solutions. And that's interesting. But what's more interesting is that we haven't used this initial temperature yet, right? So we have found this infinite family of solutions to the boundary value problem without any attention to the initial temperature distribution yet, right? So here is Fourier's leap. Fourier's leap is that, well, if you just take an infinite sum of these guys, right? This should solve. It should fit the initial condition function. Given appropriate choices of B sub n. What happens when you plug in time 0 into this infinite series of boundary value solutions? So this is just gone, and you get sine of nx. So he's saying set that equal to f of x. Now how do you find the b sub n's which are appropriate to choose? Well, what you do is you expand f of x as a Fourier series. In fact, the solution has been presented here as what's called a Fourier sine series. There's a well-defined way of expanding f of x in the same way. So you calculate these things called Fourier coefficients by doing certain integrals of f of x with respect to sine over the integral from 0 to pi. And you can expand f of x in the same way, and then you just equate coefficients, and there's your solution. Now there's a giant analytical leap here in the sense that basically Fourier is making this claim that you can represent functions as infinite sums of sine functions, which was not well-known mathematics. I mean, people had tinkered with it before Fourier, like Euler, of course, and others. But it was only in the mid-19th century work of Dirichlet and others that put this on a firm footing. But the analysis here is rather involved. But that's why the method of, so basically that's a sketch of how you do it. You separate variables, you find this infinite family of boundary value problems that have solutions, you take a formal sum of those things, and then to fit the initial condition function, you have to find the Fourier expansion of it. You fit it, and that's it. That's the one method. This is the so-called separation of variables method. There's about a dozen different flavor variations of this. You can solve Laplace's equation with essentially the same idea. You can solve, many classical partial differential equations fall prey to the method of separation of variables. I think the question of how general separation of variables is, as to, in other words, to what extent does it apply and what's the universe of problems that it can solve, I think that's an open question from what I can tell. You can also solve these with Laplace transforms. Like here, I'll show you that and we'll stop there for this semester. This one's pretty easy. Not the heat equation, mind you. We'll solve a wave equation by Laplace transforms. So this is this book I'm looking at right now is I've been spending some time in this semester. My 495 course. It's Elementary Applied Partial Differential Equations by Richard Haberman. It's a pretty good book. I like it. I've learned a lot from it. I still have much to learn about partial differential equations for sure. But here's the PDE wave equation, one-dimensional, partial squared u, partial t squared equals to c squared partial u partial x squared. C is obviously the wave. in the boundary, so here's the wave equation. And here's your boundary condition. Just that u of 0 comma t equals to f of t. All right. And the initial condition is that u of x comma 0 is equal to 0, and partial u, partial t of x comma 0 is equal to 0. So we take the Laplace transform of the partial differential equation. So the Laplace transform basically here of u is equal to big, so this is a variables. So u is a function of x and t. Take the Laplace transform of it, you get big U of x comma s. So basically we're transforming the time variable. So long story short, the Laplace transform of like partial squared u partial t squared, well, let me start out small. Partial u partial t is what? It is s times big U, right? Minus what? Little u of x comma 0. The Laplace transform of the second partial derivative with respect to time will be s squared times big U minus s times u of x comma 0 minus partial u partial x at x comma 0. Oh, I'm sorry, not partial u partial x, but what? T, yeah, thank you. But this problem is very nice, right? Because we're given what? Those are 0, right? So by now, when you see a Laplace transform problem with initial conditions being 0, you're like, well, thank goodness. I just cut your work in half, didn't I? Okay, so then here's the flip side. Basically, when you think about taking the Laplace transform of the partial derivative of the respective variable which is not transformed, you can bring the derivative inside the transform. So long story short, the Laplace transform of partial squared u partial x squared is just the partial derivative of the transformed variable with respect to x squared, just the same. Because we're transforming the t variable, nothing happens to the x variable, so the partial derivative with respect to x remains just that. So we get what? This becomes s squared big U equals to c squared uxx by the Laplace transform. And what else do we get with, let's see here, we've already used what data? We've already used our initial conditions, right? But we also, this is the interesting thing, we also have to take the Laplace transform of that boundary condition to find out what it becomes in the frequency domain. So we take the Laplace transform of this, what do you get? You get u of 0 comma s, right? Because x is equal to 0, the t is transformed to s, and then equals the Laplace transform of f of t, which we'll just call big F, right? So check it out. I mean, this is really cool because, well, that's just a first order differential. I mean, that's it's an ODE is my point. It's a differential equation in x, a second derivative in x, right? Let me rewrite this a little bit. You guys can all solve it, I think. So this becomes u prime prime minus s squared over c squared u equal to 0. Write down the characteristic equation, right? So lambda squared minus s squared over c squared equal to 0. So that tells me what? Lambda squared is equal to s squared over c squared. So that tells me that lambda is plus or minus S over C, right? I'm assuming C is a positive constant. So what's my generic general solution is U of, x comma S, excuse me, the other way around. Wait a minute. Yeah, x comma S is equal to like A. Oh, you know what? I think it pays off here to use the Cauchy-Lynch solutions. So let me do that. Do I want to do that? Not sure. I'll stick with exponentials. Fine. E to the, what is it? E to the S over C plus B to e to the minus S over C, right? What have I done? Oh, I'm an idiot. Times what? I mean, if I tell you the differential equation is y prime prime plus 3y prime plus 4y equals to 0, and then you tell me the solution is y is equal to c1 e plus c2, let me make this a 4 and that a 3, sorry, it's my dyslexia again. If I tell you that this is e to the 1 times e to the 3, and then like how many points am I going to take off your solution? Like a lot. Like half credit. So at the moment, I'm in a lot of danger of losing points over there because I have neglected a very important thing. If this is a differential equation in time, it's t and t, right? Or if it's an x, x, and x, right? This is a differential equation in x, right? So I'm missing times x times x. Important. And then, not enough time. Let me get to the point here. So you throw this out, unbounded. So that's no fun. So get rid of that. And basically this here is what we keep. But you notice that u of x comma, where'd it go? X comma, good grief. U of 0 comma s is what? Plug in x equal to 0 into this, what do you get? Just b, right? But that's also equal to f of s. So therefore, u of x comma s is equal to f of s times e to the minus s over c times x, right? And then, oh, but we can take the inverse Laplace transform. I mean, I think we can take the inverse Laplace transform of this, right? Because it's one of our theorems, right? If we have f of s times the exponential, we take the inverse transform of this, what do we get? It should be what? It should be f of, let me rewrite this a little bit differently. It's easier to see this if I rewrite it as minus x over c times s. See, that's usually what we have. We have like f of s times e to the minus as, right? So here, the quote-unquote a is x over c, right? So we get u of t minus x over c, and then u of t minus x over c. That's exactly the Dalembert solution, written in a slightly screwy way. But yeah.
Could you explain the unbounded part while we threw that out?
We were throwing this out for physical considerations. That will lead, like when you try to inverse transform it, it's going to be good for negative time or something like that. It's not what we're interested in. So physical considerations removes that. Admittedly, I haven't really explained that very deeply.
So you just like knew later down the road that would happen.
I read the book, but yeah. But yeah, I mean, I don't have a deep understanding of this at the moment. Page 581 to 582 of Haberman. This book can be yours for tens of dollars, maybe $10. Because I have the, I think I got this one for $6. $6, third edition of elementary